Hi, today we will learn how to use Aspen HYSYS and Aspen Shell and Tube Exchanger version 10 to help us in the design of heat exchanger. So this is the case that we will solve. In this case, we are tasked to design a heat exchanger to subcool condensate from a methanol condenser from 95 degrees to 40 degrees Celsius. The flow rate of methanol is given, which is 100,000 kilogram per hour, and then as a coolant, cooling water is used, and the temperature of the cooling water increased from 25 degrees Celsius to 40 degrees Celsius. And then by manual calculation, we can determine the exchanger duty. And then since the cooling water is more corrosive compared to the methanol, so the cooling water is assigned to the tube side. And then the specific heat capacity of methanol, we can find this from reference book. The value is around this much. And then we can determine the heat exchanger duty by using Q equals to mCp delta T of the methanol. So the duty of the heat exchanger is roughly 5,998 kilowatt. By knowing the heat exchanger duty, we can calculate the heat transfer area required. Before that, we need to determine what is the mass flow rate of the cooling water. The specific heat capacity of the cooling water is 4.2 kilojoules per kg degree Celsius. And then we use the heat exchanger duty that we have calculated here to determine the mass flow rate of the cooling water. So the calculated mass flow rate of cooling water is 95.21 kilogram per second. And then following the guideline, the log mean temperature difference for our system is 31 degrees Celsius, and then we select the shell and tube heat exchanger configuration to be one shell pass and two tube passes. We can check this by doing the correction factor, the air factor and the S factor. And then by using the correction factor chart, we can determine that the correction factor is 0.85, which is sufficient for our system. And then this correction factor chart relates to the type of shell and tube exchanger. In this context, is one shell pass and two tube passes. So the corrected LMTD, the log mean temperature difference, is 26 degrees Celsius. And then by using reference book for our system, methanol and water, we can select an appropriate overall heat transfer coefficient as our first trial. Here we use U0, overall heat transfer coefficient of 600 watt per meter square Kelvin. And then we use the Q equals to U0 N0 times LMTD. We will be able to estimate what is the heat transfer area required, which is in this case is 385 meters square, around 4,138 square feet. And then we follow the steps to design the heat exchanger, and the followings are the result. The outside diameter of the tube is 1 inch, and then the BWG, which refer to the thickness of the tube, is 12. And then we select the standard tube length from these options: 8 feet, 10 feet, 12 feet, 16 feet, 20 feet, and 24 feet. We select 20 feet, and then we will obtain the area per tube is around 6.28 feet square feet, and then the number of tubes required is around 658 tubes. And then we choose the type of pitch. Here we choose triangular pitch, and then based on the standard timah size, the required shell inside diameter is around 37 inch, and then with this 37 inch of shell inside diameter, we can put 664 tubes. And then the heat exchanger type, the chosen heat exchanger type is the AEL. So this is the summary of the tube specification. Number of tubes is 664. The tube layout is triangular, 30 degree. The tube material is carbon steel. the pitch is around the pitch is 1.25, the tube offset diameter is 1 inch, and the PWG of the tube is 12. And then the baffle cut is 0.2, baffle spacing is 16 inch, and the shell diameter is 37 inch. So now our task is based on the design specification here, the tube specification, the shell and baffle specification, and we need to use Aspen HYSYS and Aspen shell and tube exchanger to determine whether this specification is sufficient to exchange the duty that was determined at the beginning of the case. So what does it mean by doing the rating or checking using the Aspen shell and tube exchanger? So the rating or checking, right, will answer the following questions. Firstly, will this exchanger handle the specified duty? So with the specification, the tube specification, the shell and baffle specification, will this able to meet the duty required? And then, if so, how much of the over surface does it have? And if not, how much is it under surface? So in order to do this rating or checking in the Aspen shell and tube exchanger, the required input firstly is the fully specified geometry, which is the tube specification, the shell and baffle specification. The process inlet and outlet conditions also must be known, and then the required heat duty must be known. The allowable pressure drop also must be known. The physical property data for each site must be known, and the fouling resistance must be known also. And then when we do this rating or checking using the Aspen shell and tube exchanger, this will be the main results of the calculation. It will tell us the required heat transfer area to perform the duty, and then the calculated pressure drop, and also the actual area over the required area. So how do we go about doing this rating or checking using the Aspen? I will show you in the following steps. Okay, so now we need to create a new file for the Aspen HYSYS simulation. Click new, and then we need to define firstly the component inside the simulation. We have methanol, we type methanol, and then the second component is water. So we have these two components inside our simulation file. The next step is to define the fluid packages. Here on the left side, you can see the fluid packages is still in red color. That means we need to define the fluid packages. Okay, let's define the fluid packages. Click add, because in this case we are not doing any separation, so the selection of fluid package is not very important. So at this stage we can just use an RTL. You can also use other fluid package like Wilson also for our methanol water system. Okay, after you select, you can see here on the left side all turn into blue, so that means we can enter the simulation environment. In the simulation environment, firstly we need to define the stream. Okay, so one stream, another stream. In total there are 4 streams. To define 4 streams. Okay, stream number 1 is the methanol in. Okay, methanol in, then the composition we need to define the methanol to be pure methanol, there's no water. Okay, and then the molar flow rate, the mass flow rate is known, which is 100,000 kilogram per hour. And then because is the methanol, right, comes up from a methanol condenser. So what does this tell us? This tells us that the vapor fraction of the methanol is 0, is at saturated liquid. Okay, and then the temperature is known, which is 95 degrees Celsius. Okay, and then the pressure will be calculated. The mass flow in our case is 100,000 kilogram per hour. Okay, so all fully specified. You can see here the stripe turn into green, so that means already okay. That is the methanol in. Now let's define the methanol out. Okay, we can change the stream name into methanol out. Again, we repeat, the composition is pure methanol, no water. And then the mass flow is the same, 100,000 kilogram per hour. And then the pressure is the same. We can take it as in the beginning that there's no pressure drop. So the pressure is the same as the inlet pressure of the methanol, which is 301.4 kilopascal. So we can define here as 301.4 kilopascal. And then the out temperature for the methanol is 40 degrees Celsius. Okay. So we already fully defined the methanol, the two methanol stream. Okay, so now the next thing is we have to define the cooling water in. Okay, I will change the stream name into CW in. And then composition is only water, so methanol is 0. Okay. And then the condition here, usually we'll use the cooling water at atmospheric pressure, so it's 1 atm. And then the temperature is 25 degrees Celsius. Okay, and then the mass flow, right, will be calculated, okay, by using the mass balance. So we don't need to define that. Then the next one is to define the cooling water out. Again, we define the composition. The methanol is 0, the water is 1. Then the condition, the pressure, we are assuming there's no pressure drop at this point, so it's also 1 atm. And then the temperature of the outlet for the cooling water will be 40 degrees Celsius. Okay. Then now we need to select the correct heat exchanger. So we'll be using this heat exchanger. We click, we drag into the simulation environment. And then we connect all the stream. As we have already mentioned, the stream flowing inside the tube will be the cooling water. So the tube side inlet is the CW in. The tube side outlet is CW out. The shell side inlet is the methanol in. And then the shell side outlet is methanol out. Okay. Once we fully define all the stream, you can see here at the bottom that the stripe, right, turn from yellow into green. That means this unit, this heat exchanger E-100 is already fully specified. Okay, so now we can look at the results. What is the flow rate of the cooling water? Okay, the flow rate of the cooling water, the one that has been calculated, is 3.272 times 10 to the power 5 kilogram per hour. Let's compare this to our calculation. In our calculation, okay, the flow rate of cooling water is 342,000 kilogram per hour, okay, which is quite near to the one that is calculated in Aspen HYSYS. And then the duty, we can also check. The total duty is 2.076 times 10 to the power of 7 kilojoule per hour. If we compare this to us, after we do the conversion, the result should be quite similar. Okay, it's around 6,000 kilowatt. Okay, so as you can see, our manual calculation is similar to the simulation results in the Aspen HYSYS. We can also compare the log mean temperature difference, the LMTD. This is the corrected LMTD calculated, and also the uncorrected LMTD. Okay. The design of the heat exchanger here in the Aspen HYSYS by default is 1 shell pass and 2 tube passes. So you can check here, two tube passes and 1 shell pass. Okay, so we can compare that the uncorrected LMTD is 30.7 in this Aspen HYSYS, while in our theoretical calculation is 31 degrees Celsius. Again, very similar. And then the corrected LMTD is 25 degrees Celsius, and then in our theoretical calculation is 26 degrees Celsius. Again, very similar. We have already completed the Aspen HYSYS simulation. The purpose of the Aspen HYSYS simulation is to generate the physical property data for each site, the tube site and also the shell site, and also to define the process inlet and outlet condition, and also to solve the required heat duty. So all these will be used in the Aspen shell and tube heat exchanger. So now we need to open another software. So instead of Aspen HYSYS, you'll be using Aspen shell and tube heat exchanger. Okay, the name of the software is Aspen Exchanger Design and Rating. Here in this case, I'm using Aspen Exchanger Design and Rating version 10. Okay, let's open. Then we'll run, and then we create new, click new, and then this window will open, and then we select shell and tube, then we click create. Okay, this will bring us to this environment. So firstly, we need to import the result of the simulation, the Aspen HYSYS simulation. How to import? We go to file, we select import, and then import from Aspen HYSYS version 10. And then just now I save my simulation, Aspen HYSYS simulation, in my desktop. So I open this Aspen HYSYS simulation tutorial EDR, the one that we have just completed. Open. This new window will come out. We select OK, and then this one will also come out. Methanol is the hot side and the cooling water is the cold side, so these are correct. Use all the properties, then we select OK. Okay, once we select OK, you can see here all the folders on the left side. There's no red color, there's no cross. That means it's already fully specified, because here we are still in the design or sizing mode. But what we will do in this Aspen Exchanger Design and Rating is not design or sizing. We'll be doing rating or checking. So we have to change the mode into rating/checking. Change the mode. Then you can see here on the left hand side, okay, the folder, there are a few crosses. This means we have to define some of the variables in these crosses. Okay, the first thing that we need to define here is the geometry. Okay, the thema type that we will use is AEL, as we have already specified in our heat exchanger specification here. The thema type is AEL. So let's specify the thema type into A. This one is correct. E, 1 pass shell. Then the rear one is L. Okay, the tube layout is use existing layout. Location of the hot fluid. In this case, the hot fluid is the methanol. The methanol will be flowing inside the shell. Okay, so you have to change this into the shell. The tube outside diameter is, this is the tube specification, is 1 inch. So let's specify this to be 1 inch. The tube pattern is 30 triangular, correct. Tubes are in the baffle window, correct. Baffle type is single segmental, horizontal. Exchanger material is carbon steel. Okay, correct. Now let's define the shell specification. From our previous simulation, the hand calculation, the shell inside diameter is 37 inches. So let's specify this into the Aspen EDR. Shell inside diameter is 37 inch. And then the tube length is 20 feet. Let's specify 20 feet. Change the unit into feet. Specify 20 feet. The baffle spacing is 16 inches. Okay, 16 inches. Specify 16 inches. Okay, here the exchanger geometry is still cross, so we need to specify the geometry summary. AEL is correct. Exchanger position horizontal. The shell inside diameter is 37 inches. Correct. Shell diameter is 37 inches. Okay, and then only one shell pass. The number of tubes is 659. 659. And then the length is 20 feet. Correct. The outside diameter of the tubes, because we are using BWG, the Birmingham wire gauge of 12, this correlate to 0.109 inches of thickness. Okay, so let's specify this in our simulation. The thickness is 0.109 inches. Okay, and then we have 2 tube passes. We specify 2 tube passes. The pitch is correct, 1.25. The pitch is 1.25. Triangular. The spacing, the baffle spacing is 16 inch, correct. And the baffle cut is 20%. So we need to specify here the baffle cut is 20%. Okay, all already fully specified. Now we can run this design and rating. So we click run. Okay, there will be some warning messages here. We need to be reminded that we haven't taken into account the pressure drop, the allowable pressure drop, so we haven't taken that into account. Okay, and we also didn't input any fouling resistance. It's very important to define the fouling resistance. Okay, and then here the tube count from the tube layout is 693, the effective is 659. So let's look at the overall summary. Okay, one of the very important heat transfer parameter that we need to look through is the actual area divided by the required area. Okay, the ratio between the actual area and the required area. Here in this case, our actual area is 1.3 times the required area, which is good. We need to have higher actual area compared to the required area, but we cannot have it too much. The recommended is usually just higher than 10%. But again, we need to be reminded that we haven't taken into account about the fouling resistance here. Once we include the fouling resistance, this ratio will be lower. Besides that, we also need to compare the overall heat transfer coefficient. The overall heat transfer coefficient that we use for our first trial is 600 watt per meter square Kelvin. And then the calculated one is 948, which is 30% larger. Again, this is not recommended. Okay, this can be seen by the difference between the actual area over the required area. So another iteration must be done by using this new overall transfer coefficient to obtain a more optimized heat exchanger. So that is how we use Aspen HYSYS and Aspen exchanger design and rating to help us in doing the rating or checking of our design heat exchanger. So that's all. Thank you.